All right, let's take a look at a mass spectrometer style question that involves multiple stages being described, not necessarily all of them, but at least gives you a flavor for what these can look like. This question describes a doubly ionized ion. Kind of seems redundant, but it basically tells me this, that the charge on this thing is going to be 3.2 times 10 to the minus 19 coulombs. That's 2 times the elementary charge. It's accelerated from rest by a potential difference of 3.86 times 10 to the minus 3 volts in a mass spectrometer. Then in the ion separation region, the ion is deflected by a radius of 4 centimeters by a magnetic field of 7.20 Tesla. Calculate the mass on the ion. All right, I really am a big fan of sketching out what just happened here in cartoonish style picture. So here's what I see this question describing. We have a region here we call the acceleration chamber, in which they describe some sort of charged plates, that one and that one, in which we put a charged particle that has a velocity of 0 to start with, and that thing just gets faster as it moves through here until it comes out with a certain velocity. We're not sure what it is, but that is the acceleration chamber, and that's what's going on here. They tell us the voltage, 3.86 times 10 to the third volts across the two plates. Okay, that's the first part of what's going on here. Then they skip the ion selection or the velocity selector, and they go right on to the ion separation chamber. That's okay. Let's just go with what we're given. And so we have a magnetic field, and in that magnetic field, this charged particle comes flying out of here with a high velocity. Then it enters this region and curves through a radius equal to 4 centimeters, 0.040 meters, because of a magnetic field in this region that happens to be 7.20 Teslas. We're starting to get a complete picture of what's going on here. And the key is we have really two sections of things going on. Here we have that acceleration stage of the experiment, in which we have the voltage causing a change in energy on our charged particle, increasing its kinetic energy. So 1/2 mv final squared minus 1/2 mv initial squared, but the initial velocity is 0, so we don't have to worry about that. So we have that going on there. Then we have the second region in here, in which we have a magnetic force causing circular motion. So Fm equal to Fc. So we can start to pull out different equations and inequalities where it's necessary. Let's just remind ourselves we're after the mass of the electron. So I see the mass shows up here. I also know if I pull the formulas out of these two equations, these two forces have formulas that we can find the mass as well. So we see the mass here, we see the mass here. And you would think, well, there's two ways we can solve for mass, except that even when we cancel one of these velocities here, there's a velocity here and a velocity here. And nowhere in our question do they straight up tell us the velocity of this object. So this is a bit of a problem, but we've seen things like this before. If we pull out or write out this formula a little more clearly, the change in energy, we'll call that 1/2 mv final squared divided by the charge. Over here, well, the key is we got to get rid of the speed. So I'm going to write a formula for speed over here. Speed, little v right there. In fact, it's speed squared is equal to 2 times the voltage times the charge divided by the mass. Check for yourself, but that's the rearranged form of this equation where I rearrange it for speed. Remember, this is lowercase v, this is uppercase v. Over here, I can write a formula for speed that says speed is equal to q times b times r over m. And to make my life a little easier, I'm going to square everything in here. So V squared is Q squared, B squared, R squared, M squared. Why did I do that? Because now I can take this equation for V squared and this equation for V squared, and I can equate them. I can put those two things together and say this formula here is equal to this formula here. So I am going to carve off a little piece of my page over here to do the rest of this. So if this is a formula for speed, 2 times the voltage times the charge divided by the mass. And this is also a formula for speed squared, Q squared, B squared, R squared over M squared. We can cancel a mass to make our life a little easier. And rearrange for mass. Mass should equal, well, we can get rid of a Q while we're at it too. Mass should equal Q B squared R squared over 2 times the voltage. So neat little math trick here just to get rid of one of the unknowns. When we have two formulas with two unknowns, we can put them together and get rid of one of the unknowns at least. And now we're left with a formula for mass where I think we have everything. It's a doubly ionized ion. I'm going to run out of room here, but it's 3.2 times 10 to the minus 19 coulombs multiplied by 7.20 squared. If we're done with this stuff over here, I'm going to get rid of it. There we go. Multiply this by the radius squared, which is 0.04 meters squared. And divide this whole business by 2 times the amount of voltage. I don't like that scientific notation. That's 3,860 in my books. So 3,860 volts. All right, biggest thing is I got the squareds right. Before I do any calculations, Q, B squared, R squared, 2 times the voltage. And we get an answer of 1.19. We'll put 2 significant digits, probably appropriate. 1.2 times 10 to the power of minus 23 kilograms. All right, so again, pretty typical of mass spectrometer style questions, Thomson's experiment type questions, where it's really an opportunity for you to go back and recall what you learned about charged particles in electric fields, what happens to charged particles in magnetic fields, and also make a connection between the math and physics of those two situations. And again, we could have had a third part of this, which was the ion selection chamber, or sorry, the velocity selector chamber, and we could have had something going on with this perpendicular electric and magnetic fields. Didn't have it in this case, which makes it a little easier to go through the analysis of this question. But as you can see, definitely needed some interesting math, some systems of equations in order to allow us to calculate ultimately what the mass was.